Welcome everybody to the latest edition of the Physics Corner, a video series in which we show students how to set up and solve introductory physics problems. I'm your host, Dr. Christopher Cirola. In a previous video, we talked about how to work with the frequency or pitch of sound waves. In today's video, we're going to take a look at an idea called intensity. So intensity in general is the amount of power output divided per unit area. So in other words, how concentrated is the power, if you will. And that idea can be used for several kinds of physics problems. In separate videos, you might encounter it with light. But today we're going to talk about sound. Now, sound also has a specific kind of unit that's involved with it called the decibel. Probably heard of that as well. Decibels are related to logarithms of the power 10. In other words, a change of a decibel is related to how many times more intense the sound is, instead of just simply talking about how much more it is in additive terms. And it's kind of funky, and we'll talk about exactly how that works as we go along here today. But let's take a look at our problem, and as we work the problem, we'll introduce these ideas. So today, let's imagine you are standing or seated 5 meters from a speaker, which is about 16 feet, and you're listening to a sound that is at an intensity of 70 decibels. Again, we're going to discuss what a decibel is coming up. Then you have to, for whatever reason, move to a distance of 50 meters from the speaker. So here are our questions to address today. What's the intensity in units of watts per meter squared, that is, when you were at the 5 meter distance? And then, now that you've moved to 50 meters away, what's the intensity in both watts per square meter and in decibels at this new 50 meter mark? So let's begin. So as usual, we go ahead and talk about our known and unknown quantities, because that will help us define what we need to know. So we'll call it R1 for the first distance, and that'll be 5 meters. R2 for a second distance will be 50 meters. Now, if you prefer to use little letter d for distance, I won't stop you. It's not a big deal. But I like R myself. It's a radial idea, and most of your textbooks will do it that way. We're also talking about an intensity of 70 decibels at the 5 meter distance, so I will call that I1, and that will be 70 dB, like this. So decibels. By the way, if it sounds kind of familiar to talk about, or vaguely familiar to talk about a decibel, first off, deci is a prefix that means 10. We'll see why in a moment. And Bell is related to Alexander Graham Bell, as in the inventor of the telephone, who was actually originally trying to create a device that was useful for hearing impaired people. So let's get started. So the unknowns then are the intensity in units of watts per square meter for I1, and the intensity at a distance of I2 in any kinds of units. All right, so what are the equations that we need to play with in order to solve a problem like this? First thing is, notice that the decibels isn't a different kind of quantity, it's really a different unit. Even though there's an equation associated with using decibels, and it looks like there's a new thing that you're calculating, you're really not. What you're really doing is expressing it in a different format. This does happen occasionally in other places too. For example, if you were to talk about the brightness of a star in astronomy, they have a quantity called visual magnitude, which is related to luminosity or and intensity and so on and so forth. So they play some similar sort of games, but we'll deal with them in separate videos if we want to. We're working on sound here. So the sound quality, or the intensity in units of decibels, is this particular formula here. Let me write it out, and then I'll tell you what you're looking at. So I for intensity, and again, that's in watts per square meter, or how concentrated the power is. And I have an I naught in this formula, and what's that all about? I naught is what we call a reference intensity, or a reference number. In this particular case, the units were chosen, at least ideally, to be the softest possible sound the person could hear. Now, again, that's ideal. Most of us actually don't approach that ideal, and for a whole variety of reasons, of course. But that's the general idea, is that a normal person with really good hearing would not be able to detect sounds softer or quieter, if you will, than this. And it doesn't really matter that we chose that in that particular case, as long as we have some reference to choose, okay? So if you notice, there's a couple of things going on in the formula. Log, as in power 10 logarithms, as in what's the power of 10 of the ratio inside the parentheses here. That will come in important. Second thing, notice that it is a ratio. It's whatever intensity we're discussing compared to this reference. Now, you can do this in other ways. You can talk about, you don't have to use the reference intensity directly, but if you want to use the specific numbers that come with the decibel scale, this is what you do. And here's where the deci prefix comes into play. Notice there's a 10 in front. This is more for, say, appearances almost than anything else. It's similar to, say, you're buying some item and it says it's $19.99 instead of $20. It makes you, they're trying to make you think of something else besides what it really is. Not so much here. It's more of, if we have, say, a sound that's in 70 decibels, that's a little easier to digest and understand than, say, 7 decibels or 7 bells, if you will. So that's one formula we have. Now, there is another formula I'm going to introduce, and that's the definition of intensity itself. So this is a unit thing here. This is actually not a formula to calculate intensity originally. This is simply a transformation of units from watts per square meter to decibels back and forth. But what is intensity itself? Intensity in general is power output, so use capital P for power, per unit area, like that. Now, if the source is what we call a point source, if the sound waves are coming from a very localized point or position so that they go equally well in all directions, and again, of course, this is an idealization, then we could say it's the power output divided by the area of a sphere. What is the area of a sphere? 4 pi r squared. By the way, why a sphere? Because as the waves from a source propagate outwards, they will propagate equally in all directions in what we might say are spherical shells. So we can imagine the sound waves coming from an object going off like this. And at any particular position, say here or here, you'll be able to detect a certain amount of sound waves as they're spread out. If you're closer to the source, then the sound waves haven't spread out much and they're very concentrated. If you're far from the source, then the waves have had further to travel and spread out, and so they're not as concentrated. And that's sort of the idea. All right, so the first question is about transformation of units. So we have 70 decibels. We want to find out what the intensity is in watts per square meter. So I chose to do it this way to show you how to manipulate this equation to our benefit. So again, intensity in terms of decibels, I'm writing it like this on purpose, equals 10 log of I1 in this case over I0, like that. By the way, if you look in a textbook, you might see this symbol used for the decibels. That's what I'm calling here. And the reason I'm doing it this way, which is not standard practice, is to show you that this is just a unit transformation. This is not a separate quantity. It's just a transformation of units. So I want to emphasize it that way for our purposes. All right, anyway, so we look at this equation, and I could even throw the numbers in right away if we want to help us figure this out. So we'll have 70 decibels here equals 10 log, then I1, which is our unknown, remember. I1 is known in decibels, but it's not known in watts per square meter, divided by 1 times 10 to the minus 12th, and then watts per square meter right there, like that. Okay, so how do we go about this? The first part of the calculation is pretty easy. 70 divided by 10 to move that over. So we now have log of I1 over 1 times 10 to the minus 12th. Now, just for the moment, I'm going to leave the units off. We know that they're watts per square meter in here. We'll put those back when we come to them. I'm just saving some space and time. And of course, 70 divided by 10 is 7. All right, next step is to undo the log. So logs, base 10 logarithms are basically take a number and find out the exponent if that number was, say, 10 to that exponent. So the number 10 is 10 to the power of 1. So log of 10 is 1. 100 is 10 to the power 2. So therefore, log of 100 is 2. That's all that's going on. Which means if we want to undo, reverse engineer the logarithm, we need to take everybody to the 10 power like that. So that's what we'll do. So we take 10 to the log of I over I0. And again, I'll just write this way to save some space for the moment. And it equals 10 to the power 7. You have to do this on both sides, right? It's just like any other transformation or calculation or operation that you perform on an equation. You have to do it on both sides at the same time. So 10 of a log cancel each other out, and it's I divided by I naught like that. 10 to the 7th power, or 1 times 10 to the 7th power, looks like that. Last trick, let's multiply both sides by I. This should be I1 and I naught over here. So 1 times 10 to the 7th power multiplied by I naught. 1 times 10 to the 7th, 1 times 10 to the negative 12, and I get a 1 times 10 to the positive 5 watts per square meter, like that. Okay, so let's review what we found out and see if it makes any sense. First off, take a look at this transformation here, this calculation. When you work with exponents, 10 to the 7th, 10 to the minus 12th, you might remember this rule. You add the exponent, so 7 minus 12, and that'll of course be a minus 5. That's how I should say it, like that. Okay. Now, one thing we've noticed, if you look carefully, it's 7 powers of 10 greater than the reference, right? 7 powers of 10, go back to our original formula, multiplied by 10 gives us a 70 decibels. Okay. So that's a way to show how these weird kind of decibel units work. Again, they're chosen in part for convenience. As weird as it sounds and as the convoluted as the calculation we just did sounds, the upside is that the actual numbers for decibels are things that are a moderate size, so we can understand a little better. Again, it's kind of easy to understand the number 50 or 70 or 100, numbers like that, rather than say, oh, it was 1 times 10 to the minus 5, or 1 times 10 to the minus 7, or 1 times 10 to the minus 12, right? So that's partly why we do it this way. Okay. Now, next is the change over to the other position. So, now in this case, again, we have a source of sound waves right here. We can imagine you, the observer, are right here, and this is distance here is our 5 meters, like that. But later on, you move to a wholly different position, and I'm not going to sketch in the entire circle just to give you an idea how big it must be different here. This position is now a distance of 50 meters, right? So that's the idea. So what this means is this: intensity in general is power over 4 pi r squared, like that. Okay. This is what we call an inverse square law. And there's a couple of different ways to go about this. I'm going to give you the short version of this. It means that it goes as the square of the distance. Okay, so if I get 2 times further away, and I want to know how much the sound intensity has dropped, 2 squared is 4. So it's 4 times smaller, or 1/4. If I move 3 times further away, it's 3 squared, or 1/9 of what it was when I was closer, and so on. Well, what's the ratio of R1 to R2? That's 5 meters to 50 meters, right? And if we want to simplify that, that's a ratio of 1/10. If this is an inverse square law, then the ratio that counts is this, goes as the square, notice, and that becomes 1/100th. So I2 equals 1/100th of I1. Okay, now always, when you think of doing physics problems, make sure we can do these in the proper order or get a sense of what the numbers mean. Now, the specific numbers might be a little foreign to us at this stage, right? That's fine. But you should have a feel for whether the numbers should be bigger or smaller, right? And it makes sense if we come up with a result that says, oh, the sound waves I heard when I was further away from the speaker should be quieter, should be softer than the sound waves I heard when I was closer. It should be louder when I'm closer and softer when I'm further away. So we should expect to have a smaller number when we do that. So let's find out if we do. So 1/100th, and remember it was 1 times 10 to the minus 5th watts per square meter, right? 1/100th, that's 10 to the minus 2, if you will. So if you want to write out this way, just to reflect what we were doing before, and might as well do that. Again, when you handle exponents like this, the minus 2 and the minus 5, it's an additive property for the exponents. -2 and a -7 together are, or excuse me, -2 and -5 together are -7. So 1 times 10 to the -7th watts per square meter will be our answer for that intensity. Okay, last trick is to change this into units of decibels. So what does it look like? We talked about the sound wave being, or the sound intensity, being 70 decibels when you were 5 meters away. What is it in decibels when we're 50 meters away, right? So let's go ahead and do that. So the intensity in decibels, again, is 10 log, and that'll be the intensity in watts per square meter divided by our reference intensity. So 10 log, we have 1 times 10 to the -7. In this case, I do want to write the units just to show what happens to them. So 1 times 10 to the -7th on top, 1 times 10 to the -12th on bottom, like that. Notice that watts per square meter, they cancel. Now, when we're dividing exponents, we subtract the numbers. So this will be a -7 plus 12, or if you prefer, -7 minus a -12, right? So a -7 minus a -12 is -7 plus 12, or +5. So that will be this then, 10 log of 1 times 10 to the 5th. Now notice there's no units in here anymore. Those canceled. Notice I still have this 1 times 10 to the 5 here. The 1 doesn't matter so much in this case, right? It's just the same thing as this saying this. Again, remember what logs are. Logs take the exponents. So log of 10 to the 5th is just 5. So 10 multiplied by 5, and therefore our answer is 50 decibels, like that. So by increasing the distance by a factor of 10, we have dropped the sound intensity from 70 decibels to 50 decibels. By the way, I chose numbers like this because these are on the order of conversation type levels of sound that you'll hear. 50 is a little on the soft side, but it's still something you can hear if you pay attention. 70 is maybe a little bit louder, of course. Well, it is a little bit louder, but it might be something more along the lines of, say, somebody actually talking, trying to speak to an audience, perhaps, without a microphone, by the way. And that's why I chose numbers like this. Anyway, so what we have done then, to review real quickly, we have talked about the relationship between decibels for intensity units and watts per square meter for intensity units. And along the way, we also discussed what intensity itself is. Intensity being power per unit area, and if that object that's giving off the waves is emitting the waves, sending the waves out equally well in all directions, that ends up being an inverse square behavior. So the intensity of the sound drops as the square of the distance. And that is how to handle sound intensity. All right, everybody. Technical assistance for these programs is from Cindy Gelchow and Sophia Turner. Our funding is granted to us from the University of Mississippi and the University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi itself. I am your host, Dr. Christopher Cirola, thanking everybody for your attention, and clear skies.